Thanks, Alan, and good evening, everybody. It's quite an honor to be here and to be associated with the revival of the Michaud lecture series and having my name linked with people like Joseph Rothrock. It's quite an honor, and I'd like to echo Alan's comment about what a gem we have in this area. I was fortunate enough to grow up down in Gettysburg, and we spent a lot of time up here in the South Mountain area at the various state parks. In fact, I have very fond memories of my brother and myself and a couple of our friends. Every Saturday before Memorial Day, we would head up to Fuller Lake. This was back when they didn't allow swimming until 11 o'clock that Saturday. We would get up there early and we would literally fight each other running towards the water to say we were the first people in the lake to go swimming that year. So always enjoyed this area. Tonight I'm going to talk about groundwater and surface water in the South Mountain region, some of the impacts and challenges. As Alan mentioned, I'm involved with the Source Water Protection Program, and I am a geologist, so my forte is groundwater and groundwater quality and groundwater protection, but I have tried to include some information related to surface water also tonight. And I'd also like to thank Adam McLean from the Adams County Conservation District, Tammy Piper from the Franklin County Conservation District, and Vince McCollum from the Cumberland County Conservation District. They're all watershed specialists with the districts, and they provided me with some background information regarding some of the local issues that they thought would be useful to talk about tonight. And Tammy and Adam also provided some of the slides I'm going to be using tonight. So let's get right into it. Well, we can't have any kind of lecture about water or groundwater without starting out with a picture of the hydrologic cycle. Everybody's probably seen this before. I guess I should also back up and say what I thought we'd do is have just some real basic information about groundwater geology and basic hydrology to give everybody a background in it so that we're all pretty much on the same level. I realize for some of you people this is probably going to be a review and might be somewhat simplistic, but nonetheless I thought it would be useful. Then we'll talk about some of the quality and quantity issues affecting our water resources in the area, and I'm going to have to, of course, put in a shameless plug for the program that I work in related to source water protection, which is designed to protect our drinking water sources. So, of course, the hydrologic cycle is water's in constant motion. It falls down from the sky as precipitation. It infiltrates into the ground. Some of it runs off into streams. Some of it evaporates directly into the atmosphere. Some of it's transpired by plants back into the atmosphere, but it's constantly in motion. Essentially, we basically have the same amount of water we've had for millions and millions of years. It's just constantly being recycled on the global scale. And just to make sure that everybody understands what we're talking about with groundwater, groundwater is water that occurs in the subsurface in the zone of saturation. In other words, it's all the pore spaces or the crevices in a rock, which is most of the groundwater that we have in this area is from fractured rock. All those openings, voids, fractures, pore spaces, whatever they are, underneath the water table, there's no air in that. It's all completely saturated with water. Above that, in the vadose zone or the unsaturated zone, you will get pockets of air in with some of those voids. You might also get water also, but that water is held by capillary tension. It's not really considered groundwater. It moves quite differently than the way groundwater does. In fact, to use the vernacular of this day, flow in the vadose zone sucks. And the water table, of course, is a subdued reflection of the land surface. Generally, it follows a gradient. It generally discharges at a surface water body, as we'll see here in the next slide. You have, excuse me, you have an area where groundwater is recharged. It infiltrates down, occurs in the water table. Groundwater is in constant motion. Some of that movement takes very long time. Some of it's relatively short, but we're still talking about rates of movement that are much, much, much slower than the way surface water moves. And it is possible that you can have very deep groundwater flow that could take hundreds or perhaps thousands of years. But the important thing to recognize about groundwater is that it is connected to the surface water. It will reemerge at some point in a surface water body. So there is an intimate connection between surface and groundwater. So if that's one of the main things that you take home tonight, that would be great. If you just remember that groundwater and surface water are basically a single resource. You can't really divorce the two. They're intimately connected. Sometimes you might hear the terms water table aquifer or unconfined aquifer or confined aquifer. And if you're wondering what that means, basically the water table or an unconfined aquifer is where the water table is free to move up and down in response to precipitation and or withdrawal. It basically is moving under gravity where it discharges into a surface water body. That's distinguished from what's referred to as a confined aquifer or an artesian aquifer, where that water is actually under pressure. In those situations, you have an aquifer, and I guess I should define what an aquifer is. An aquifer is a geologic deposit that's capable of transmitting and yielding usable quantities of water. So that's what an aquifer is. You can get usable quantities of water out of it. So with the unconfined or the artesian aquifer, there's generally some type of a confining layer, whether it's a shale layer or maybe in some places it might be a thick lens of clay or a thick layer of clay that's capping that water, keeping it within that particular layer of the aquifer. When you penetrate that confining layer, that water's under pressure and it's going to rise above the level that you initially encountered it. And if there's enough pressure, you'll actually get the well to flow. So if you've ever heard of a flowing artesian well, that happens when you drill into one of these confining units and the water's under enough pressure that it not only flows above where you initially encountered it, but it flows above the top of the casing. And there are instances in the area where we've had flowing artesian wells. One other thing to keep in mind with the fact that groundwater and surface water are intimately connected is the streams can either receive groundwater or they can also provide recharge to the groundwater system. Basically, they have what's referred to as a losing stream. That's a situation where the stream bed is actually leaking water to the subsurface, possibly recharging the groundwater. It's sometimes referred to as an effluent stream because you're losing the water. That's distinguished from a gaining stream or an influent stream where you actually have groundwater feeding the water body, the stream. That's probably the more common situation in the area that's not involving carbonate rocks. In some of your carbonate rocks, you may have losing streams. Some of your areas underlain by shales and sandstones or crystalline rocks, you probably have the situation where it's a gaining stream. And that can also change depending on the water level. It's not uncommon during flood stages for streams to be losing groundwater or losing water to the subsurface during floods, but once the water level goes down, it goes back to being a gaining stream. The other thing to keep in mind regarding this connection between groundwater and surface water is that the base flow or the groundwater that's actually discharging into the stream bed that sustains that stream, it's probably about maybe 60 to 70%. It's at least half of the water in a given stream channel is actually discharging groundwater, which is referred to as base flow. That's the reason why in the summer, for larger streams, even though it hasn't rained for perhaps weeks or maybe a month or two, those streams are still flowing because it's intersecting the water table and groundwater base flow is discharging into that stream. Another important thing that sort of is the nexus between surface water and groundwater are wetlands. They're sometimes referred to as swamps, marshes, bogs, vernal ponds. These can usually have water in them. The water can be standing or it can be flowing, probably not very fast, but there can be movement throughout that zone. They have certain kinds of soils, what's referred to as hydric soils, and there are specific kind of plants that grow in wetlands. Again, these are areas where you're basically intersecting the groundwater table. And they're important parts of the watersheds because they're a really good job at modifying water quality. They also can help with preventing flooding by storing water or slowing the movement of it. Can also, to some degree, influence local or regional weather and climate by moderating temperatures, things like that. Also air circulation at times, depending on how large the wetland is. And it's one of the most productive ecosystems in the world. And you can find all kinds of interesting creatures in wetlands, in addition to the very specific and unique plant life that you'd find. There's also certain kind of animal species that like wetlands also. But the one thing I do want to point out is a lot of people just automatically assume wetlands are groundwater recharge areas. Actually, most of the time, wetlands are groundwater discharge areas. As you can see by this diagram, they're basically areas where the water table's been intersected or water is flowing into those things. It is possible for wetlands to recharge groundwater. It all depends on the type of physical setting and the site-specific conditions, but most wetlands, for the most part, are groundwater discharge areas, not necessarily recharge areas. So let's briefly talk about what happens if we install a well into the ground and start pumping water. As you can see by this diagram, we have a blue line that represents the water table surface, and the top part of the diagram is a cross section. The bottom part is a map section or a plan view. So what happens when you install a well and you start pumping it is you develop what's known as a cone of depression around that well, where you actually draw down the water surface, and it actually does have that configuration like that. It's sometimes referred to as the zone of influence. You can project that to the surface and kind of get an idea as to where you might see water level deflections or drawdown in an area. The one thing I do want to point out is the zone of influence and the zone of contribution are almost never coincidental. The zone of contribution can also be thought of as the capture zone for a well. If you were designing a groundwater cleanup where you wanted to pump and treat the groundwater, what you would be trying to determine is what that capture zone is, or at least trying to develop a well that would have a capture zone that would capture all the contaminants that you're trying to remove, whether you're actually trying to remove free product or whether you're trying to actually treat water with dissolved contaminants in it. But most of the time in Pennsylvania, there's a slope on the water table. It's almost hardly ever completely flat. So that zone of influence and zone of contribution are almost never coincidental. It also comes into play in the program I work in, the Wellhead Source Water Protection Program, because if you're trying to determine where the area that contributes to a well is, what you're actually determining is the zone of contribution. Some consultants and water professionals will erroneously assume that your drawdown area, your zone of influence, is the same as your capture zone. That's not necessarily the case. In fact, about the only time you would have the zone of influence coincidental with the zone of capture or the zone of contribution is if you have a circular island made of completely homogeneous isotropic material. Then it might be coincidental. But in Pennsylvania, we're dealing for the most part with fractured bedrock. So the water we're getting is out of like tiny crevices and cracks in those rocks. We don't have very many situations, at least in this part of the state, where we're dealing with sand and gravel aquifers. So we're dealing with fractured bedrock aquifers. So I just wanted to point out that distinction between the zone of influence and the zone of capture. So let's, looking at the big picture and then sort of zooming down to the local level, let's look at what's going on, or at least what we think what's going on with the hydrologic cycle or the water budget here in Pennsylvania. And what's depicted here is the water cycle and average annual hydrologic budget for Pennsylvania. You can see the precipitation is about 42 inches. Some of that is returned directly through evapotranspiration. Some of it infiltrates into the ground. Some of it runs off. And you'll see that your base flow is equal to what your infiltration is. And your base flow combined with the surface runoff gives you your stream outflow. So it sounds relatively basic, like you're doing a checking account, trying to balance these things out. But in reality, trying to determine what some of these factors are, it's not very easy to do. It's sometimes quite a challenge. But this is the average for Pennsylvania. Obviously, there's a lot of variation depending on where you're at in the state related to the type of soils, the geology you have, and the climate and things like that. And just to illustrate that, we can kind of look at these cartoons for the average annual water budget for Franklin and Adams counties. You can see that the infiltration rate in Adams County is about half of what it is in Franklin County. That's related to the type of rocks and the type of soil that's involved. Also, you can see Adams County gets a little bit less precipitation than what they do in Franklin County. Franklin County, I think, is around 42, 44, whereas Adams is about 39. That's probably related to the orographic effect of South Mountain as the weather systems, which predominantly move from west to east, move over the mountain. It loses moisture in those mountains, so by the time it gets past the mountain, it's lost some of that moisture. So we see a little bit less rain down our way in Adams County than some of the folks actually on the mountain do. And I would expect that, in fact, I did look, I couldn't find a cartoon for Cumberland County, but Cumberland County's numbers are very similar to what you'd see for Franklin County because the geology is so much similar. Speaking of geology, let's take a look at a simplified geologic map for the region. We have Cumberland, Franklin, and Adams County depicted here, and these colors represent different types of rock, starting with the oldest, which is, actually let me point out where South Mountain is on this. It's actually kind of neat. It's sort of geologically defined. If you look at the sort of light olive and orangish area, that's basically South Mountain. It's underlain by Precambrian metavolcanic rocks and Cambrian quartzites and phyllites. That's most of the rocks in South Mountain. On the western side of it, the material shown in pink is limestone. There's also some shales involved with that, particularly at some shale belts at the western edge of the Cumberland Valley. But the Cumberland Valley, or the Great Valley, is basically a large limestone valley. It runs down into Maryland, and it runs through Pennsylvania also. It's very productive farmland, but it has some interesting challenges related to groundwater that we'll get into in a minute. On the other side of South Mountain, on the east side, we have the Mesozoic Basin. It's referred to locally as the Gettysburg Lowlands or the Mesozoic Gettysburg Basin. This is underlain by red shales and sandstones, which is portrayed by the light green color. And it also has a very, very dense, hard, igneous rock called diabase, which is depicted by the red on the geologic map. This diabase is notoriously the worst aquifer in Pennsylvania. There are very few fractures in that. There's absolutely no primary porosity left in those rocks. The only water's in the fractures. It's very hard, very tight fractures. It's possible to get adequate yields for a domestic supply out of the diabase, but it's very, very difficult to develop a water source for like an industrial application or for a public water supply within that diabase itself. In fact, if you're familiar with the area that's now the Eisenhower Inn around Gettysburg, south of Gettysburg off the Emmitsburg Road, they have about 13 or 15 wells drilled into that diabase to try to get enough water out of that. It's so tight, and that's the only way they can get enough water out of that is by having that many wells drilled into it. The light and the dark blue are various different sandstones and shales. Sometimes they're good aquifers, sometimes they're not. But one of the most prolific aquifers in the area are some of these carbonate rocks, and that is partially due to the fact that in a